Welcome. In this video we are covering the basics of how to simulate material decomposition or pyrolysis in FDS. For the reaction rate of the pyrolysis process we are using an Arrhenius model as it is implemented in FDS version 6.7.6. At first we have a look at the basic parameters that are used to define the Arrhenius model. Afterwards we create an FDS input file with multiple decomposition reactions. These reactions are then used to approximate the MCC results that we have processed earlier. For the discussion on how the dataset was prepared, you can click on the card in the corner to watch the respective video. We will use the resulting FDS input file later on as a template for our inverse modeling process. In general, there is three parameters that we can change in the Arrhenius model to adjust the reaction rate. There is the pre-exponential factor A, the activation energy E, and also the reaction order N. FDS provides two different ways how the Arrhenius parameters can be defined. For the first way, the parameters can be entered directly. For the second way, reference parameters can be provided. FDS then internally transfers these reference parameters into the respective Arrhenius parameters. One needs to keep in mind that the reaction order for this method is always assumed to be 1. To set up the Arrhenius parameters, we primarily work with the Assess Pyrolysis guest notebook. There are a couple of examples at the end of this notebook how to define the Arrhenius parameters. Alright, so let's discuss how we use the reference values to set up the Arrhenius equations by going over the examples. To simulate the microscale experiments, we use a special functionality of FDS. This feature provides a simplified model to simulate thermogravimetric analysis, differential scanning calorimetry or combustion calorimetry, but we focus only on the TGA and MCC. This model can be activated by adding the TGA analysis parameter to a surface definition. This functionality can only be used at a single surface and also for a surface that only has one layer. I've prepared an FDS input file here and we will now be adding the necessary parameters. So the parameters like the mesh and time do not matter that much because the TGA analysis functionality will basically sidestep everything that makes FDS behave like FDS. It will run only a very simplified model for a mass sample that is heated up, and while it is heated up it will react following the Arrhenius model. Next, the reaction is defined, but this is essentially just a placeholder. Here is the start of a definition for a surface and a material, and also a material is predefined for the residue. Again, here most parameters don't matter because it is just looking at the mass and the temperature rise of that mass. Future Tristan here. If you're interested in the mass loss or the energy release, meaning the TGA or MCC, you can use the video as presented. However, if you're interested in the energy consumption, meaning the DSC, then you need to also specify the specific heat and also the heat of reaction, which is not covered in this video. Let's start with the material. In FDS, the pyrolysis reactions are associated with the material. Therefore, the Arrhenius parameters or the reference values are associated with the material definition. Since we want to use the reference values, we can start here, for instance, with the reference temperature. The reference temperature essentially defines where the peak of the reaction is located. For instance, I have set here 380 degrees Celsius, I could also use 250 or whatever, and if I were to run the simulation, assuming that all the parameters are implemented, I would see, for instance, for the reaction on the right hand side that the peak is located at 380 degrees Celsius. If you were to enter 250 degrees Celsius as reference temperature, the reaction would move to the left. Next is the pyrolysis range. Roughly speaking, the pyrolysis range determines the width of the peak. That means for lower pyrolysis ranges we have a narrower but taller peak, and for wider pyrolysis ranges we would have a flatter but wider peak. The next parameter that we need is a heating rate. This heating rate, defined in the material, is related to the heating rate under which the experiment is performed that we would like to reproduce here. Our goal is to reproduce the results from the MCC test that has been performed here with a heating rate of 60 Kelvin per minute. Therefore this heating rate here is set to 60. So this then allows FDS to translate the reference values into the Arrhenius parameters, the pre-exponential factor and the activation energy. So what we need now is something to allow for a combustion reaction. Remember, in the other notebook we had determined an average heat of combustion. And since we have already prepared the input lines, we can just copy these lines over. Okay, following this decomposition reaction, our material will release this amount of gas and this amount of solid residue. Now we need to make sure that our IDs for the species and also for the material fit into the definition of this input file. The material ID from the residue seems to be the correct one, but the species ID should be methane, because that is what we want to have for our chemical reaction in the gas phase. So what we need now is to change the heat of combustion from methane to our average heat of combustion. So we can just copy this value and put it into the respective line in our material. FDS allows us to have multiple pyrolysis reactions within one material. However, I mostly set up my files in a way that I have a single material for a single reaction. To make that more explicit, I set the n reactions parameter to 1. So we have our first material set up, which is essentially setting up the first decomposition reaction. We have the parameters that describe the reaction rate. We have defined how much of our material will be left over as non-reacting residue residue, and we have defined how much of the material will be transformed into a gas and what that gas is supposed to be. Furthermore, for this reaction we have also defined what the energy release is, the heat of combustion. Now we need to hook up this material to the surface definition. For the material we set up this array and only add in one parameter for now, but we know that we want to have multiple reactions so that in the end we can just extend this array. And then a mass fraction needs to be associated to this material. For now I have set it to 100% as PMMA 1. Since we want to use the simplified microscale simulation model, we are adding here the TGA analysis parameter and set it to true. In the definition of the surface we also need to prescribe the parameters of the microscale experiment that is to be conducted, so specifically the heating rate. So we set here the TGA heating rate parameter to 60 Kelvin per minute. So be mindful here, there's two different heating rates that need to be defined when you use the reference values. In the material is the heating rate, which allows FDS to transform the reference values into the respective Arrhenius parameters. So this is essentially the heating rate of the test that has already been done, that is used as input to determine these parameters. The TGA heating rate in the surface definition prescribes the heating rate of the simulation that is to be conducted. Right now it might be a bit confusing because both values are the same. That is obviously because we want to reproduce this specific experiment. It will become a little bit clearer later on when we set up the inverse modeling process, where we want to use two different simulations as target. There we would have one simulation for the MCC at 60 Kelvin per minute, but the same reaction is also used in a TGA analysis for 50 Kelvin per minute. Then we also need to define an end temperature when the simulation is supposed to stop. For that we look at our experiment data again, and we see that at about 600 degrees Celsius the experiment stopped. So it shows as the TGA final temperature 600 degrees Celsius. By the way, the start temperature is the ambient temperature defined in FDS. So if you wanted to have a different start temperature as the default, you would change the TMPA parameter. Now the basics are set up. For completeness we have a look at the rest of the file. There is an obstruction defined, on top of which is a vent that links to the PMMA material. Then afterwards is the end of the file. Alright, let's run the simulation and have a look at the results that we have generated so far. Back in the notebook we have a brief look at the top. Again, in the beginning we just import a couple of packages that are necessary for processing the information. This is then followed up with a cell that contains general information for this notebook. First a path is set up pointing towards the simulation directories, which is followed by a path that points to the processed MCC results from the other notebook here. For convenience I've also copied over the average heat of combustion. And finally an output directory is created. Here we read in the processed MCC data. This cell creates a plot which compares the MCC data and the simulation results. At the top of the cell the simulation results are read in. This is followed by a plot of the average MCC data. Finally the results from the simulation are plotted. With that then we are able to just run this particular cell and it will automatically read in the most recent results from the simulation and compare it with the experiment. Here's the plot with the energy release against the sample temperature in degrees Celsius. The blue solid line shows the results from the simulation and the gray dashed line in the background is the experiment data. It may seem here when using the reference values that one only needs to provide two parameters to control the reaction. Specifically the reference temperature and the pyrolysis range, since the heating rate doesn't change. However, that is not the complete picture. What we also need to address is the fraction of the sample mass that is related to each of the reactions. Essentially, the sample mass, in combination with the reference values and the heat of combustion, determine how the reaction peak looks like. For instance, if we were to reduce the mass connected to this reaction to, let's say, 75%, we would see a smaller peak here. We also see now that the peak should be located at higher temperatures. So I added 3 degrees Celsius to the reference temperature and also increased the sample mass by a little bit to 76%. Another thing that is maybe not too obvious in this plot is that both sides from the peak have a different slope. I think it may be easier to see here on the left hand side with the 250 degrees Celsius reference temperature. The distance from the dotted line to the right hand side is shorter than the distance from the dotted line to the left. You can also see that at the beginning and the end of the slope. Okay, back to the plot, we can see a couple of things. At first, we are unlikely to get both slopes correct with only a single reaction. The slope on the right hand side is much steeper in the simulation than in the experiment, specifically here at the end. Furthermore, there are 3 more reaction peaks visible at lower temperatures, one at about 300 degrees Celsius and 2 more at 200 degrees Celsius. In an effort to achieve a better approximation, I will now start adding in a couple more pyrolysis reactions. These will be designed in such a way that the superposition of their results leads to a better fit. Obviously, then the question arises as to how many reactions one could or should add in. In the end, the number will be a guess, with the goal being to have as few reactions as possible, yet still obtain a reasonable result. Alright, let's start by adding a reaction to the right hand side of the main peak. For this, we just copy the first material definition and change its ID to PMMA2. Then simply change the reference values. Maybe we set the reference temperature to 410 degrees Celsius so that the reaction takes place at a higher temperature. Also, the peak should be a bit narrower, so we set the pyrolysis range to 80 Kelvin. All the other parameters remain unchanged. Now in the surface definition, the new material is added to the array, and also the array is expanded by 1. Then we need to connect the sample mass. The material mass fractions could also be provided in a similar array as the IDs, however I like to have each of the fraction in its own line. We change this value to 2 to have the second component of the first material connected to this mass fraction. Its mass fraction should be significantly less than the main peak, so let's go for example with 10%. As expected, the simulation result now shows a wider peak from both overlapping reactions. Also, the slope on the right hand side is better reproduced. Still, it looks to me that the second reaction should be shifted more towards the right. This means the reaction should happen at higher temperatures, so maybe we go with 415 degrees Celsius. Yes, that looks a bit better. However, to me it seems there should be another reaction at even higher temperatures. So what I'm essentially doing now is repeating the process I just demonstrated multiple times to add more reactions. This process takes a little bit of time, therefore I will not record it. Afterwards, I will just show you the parameters that I've chosen to define the individual reactions. After a little bit of trial and error, here are the results of my approximation efforts. The results of the simulation are somewhat close to the experiment data. To improve the fit, we will employ an inverse modeling process in a future step. But now we will look into the FDS input file for the material definition. I decided here to set up 8 different reactions. Most of the material is associated with the large peak that we started with, then everything else gets less and less material. The material definitions here are basically always copies from the first one, just reference rate and reference temperature change. As a summary, these two lists contain the reference temperatures and pyrolysis ranges that are used for the 8 reactions. Anyway, if you're interested in this notebook or the final FDS input file, you can just download the dataset. The link should be in the video description. To get a better understanding of the contribution of the individual reactions, I've created this plot here. The result of the simplified TGA model is this CSV file with the _TGA in the name. It contains the data series for the different aspects of the model. The first column is the simulation time. This is followed by the sample temperature. Then the total normalized sample mass is recorded. The sample mass is then also divided into the different mass fractions for the reactions. Furthermore, the residue mass is tracked. Next to the residual masses, also the mass loss rates are tracked as the total value and also divided over the different reactions. The residue mass loss rate is essentially the production rate of the residue. And then 2 columns are added for the MCC results and for the DSC results. Basically, the total normalized mass values refer to the TGA data. You get the MCC data by multiplying the mass loss rate with the heat of combustion. So this is then what I did in the plot here. First load in the data, plot our target, then I create the list that we saw at the bottom. Then for each column label I check if MLR, the abbreviation for mass loss rate, is part of the column label. If that is the case, I am plotting the mass loss rate multiplied by the heat of combustion against the temperature. And I am simply using the column labels as data series labels. In the end, we have one reaction which covers most of the large peak. 2 reactions at higher temperatures are used to capture the slope on the right hand side. A smaller reaction is capturing this small peak here, and 2 smaller reactions capture the 2 peaks at 200 degrees Celsius. I also added 2 flat but very wide reactions. These are primarily used to smooth over some of the bumps here on the left hand side. So this reaction scheme is now forming the basis for the inverse modeling process. During the inverse modeling, the algorithm will then improve the fit of the approximation. Now let's have a brief discussion about the reaction order. As mentioned before, when using the reference values, the reaction order is assumed to be 1. If you wanted to change the reaction order, you would need to provide the Arrhenius parameters themselves, meaning the activation energy as well as the pre-exponential factor. So since FDS is computing these parameters, the question may arise, how do we get to them? For that, we would need to look into the .out file. However, if you run a TGA analysis true simulation, no out file is created. The reason is that when you use the TGA analysis true model, FDS basically sidesteps everything that is related to the basic CFD model. It runs a very lightweight model that is only computing the heat up of the material and taking the reaction rates into account. However, you can set the TGA analysis to false again and FDS runs in its normal way. I have prepared a file here in the examples for the get Arrhenius simulation. However, you need to take into account, since you are now running a proper simulation, you also need to provide proper values. Specifically, a thickness for the material layer needs to be provided. I just set up here 1 centimeter. Doesn't matter. You see also for the example case I have only one material set up. Now you can start the simulation, and when the out file is created, you can basically shut it down immediately. So here for instance we see a .out file was created and also the HRR file. If you now open the out file, we get an overview over the parameters of our simulation. information. When we scroll down, at some point we reach a section that contains the material information. In this case, it starts in line 277. Here's all the information of our PMMA1 material, which also contains the reaction kinetics parameters, the pre-exponential factor, the activation energy, and the reaction order, which you see is set to 1 because obviously we started with the assumption that it would be 1 from the reference values. We can now copy these two parameters and write them into a new FDS input file. There's another example created here for the order 1. On the left hand side I have the FDS input file, on the right hand side is the out file that we were discussing before. You see that the heating rate, reference temperature and pyrolysis range have been changed to the pre-exponential factor, the activation energy and the reaction order. And you also see that the values for these parameters are just copied over from the out file. In the notebook the last example describes the different reaction orders. The gray dashed line, which is labeled base, is the simulation result using the reference values. The blue line for the reaction order 1 is the result of a simulation where A, E and N have been defined manually. The orange line is the result of a simulation with the same parameters as the blue one, just with a higher reaction order. Anyway, that is only a side note for completion. The focus here in this work remains on the reference values. Alright, in the next video we will discuss some changes to the gas phase reaction model. So if you found this video helpful, please leave a like and see you in the next video. Bye.